Hi, welcome to episode 2 of the design project series. This being an even numbered episode, it'll be based around analog, and this is going to be the first part of the linear basics. In this episode I'll be discussing basics about using transformers with rectifiers and a short introduction to the 7800 series regulators. I'll show an example of the transformer setup as well. So we'll have a look on the scope, the 110 volt. Well, actually, we won't be seeing the 110 volt, but we'll be seeing the secondary side with a 60 Hz waveform, and then you'll see it being rectified, and then you'll see it being regulated with a 7805 5-volt regulator. And then we'll discuss a little bit about more the different 7800 family, maybe even briefly on the 7900 family. Okay, so without further ado, let's get straight to it. Okay, what we have here is a transformer. It's got a switch and a fuse already in line on the primary, and it has a dual secondary. One secondary has a center tap, and it all goes to this plug here. Now, if I remember correctly, the main center tap is, the main secondary, the center tap one, is a 24 volt, which is center tap, so it can be 12 either side, and the other secondary is a 9 volt, which I've diagrammed here. The switch and the fuse go in to create the circuit there, and these are the secondaries. A connection. Now, you must note this is plugged in, but this socket here is usually used for my soldering station. It's disconnected through the switch, so this socket is only active when the switch is on. Okay, so basically I got the test meter set up. So let's put that on AC, and let's plug it in across the 24 volt secondary, just to double check it is 24 volt. Oops, get an angle so I can see it right. Switch on the main power. And I got to switch on this way. Actually, it's around about 18 volts, unless it's wired funny. So let's have a look. Sometimes they put the secondary winding at the end. Come on. Okay, now that's in. Let's have a look. Okay, so that's 18 volts there as well. So let's okay, let's try the two end ones then. Okay, so we got that in. Let's I think I was reading like 36 volts across, so yeah, it's about 18 volts between the inside and the outside of the secondary winding. Okay, well let's have a measure the secondary, the other secondary. Okay, on there, and on there. Yeah, so it's about a 12 volt. Basically, that's what that does. Okay, I've set the system up and I've just got it running, and this time we have the oscilloscope plugged into it. Now on there it's showing 10.3 volts. Now, as you can see here, we have a 60 Hz wave, because I live in Canada and they use a 60 Hz. If you live somewhere like the UK, This wave would be a little bit more stretched out and be 50 Hz. So yeah, I've shown the measurement on here. The scope's reading on 60 Hz and the measurements are showing 60.24 Hz, but that might be because I'm off slightly. And yeah, and it's showing a 28.7 volt peak to peak on there, and 10 volts RMS on there. Now, you may have been confused a little bit by the difference between the readings on the test meter and the readings on the oscilloscope. As you can see, before, the test meter it said 10.27 volts, and the oscilloscope was 28 volts peak to peak. Now, the test meter reads what's called RMS, or root mean square, and this is basically an averaging. All test meters pretty much read like that, and when you looked at the oscilloscope you actually saw the raw the voltage. So the 27 volts is the highest to the lowest value it could be without any averaging at all. Now, to convert that to the average, basically all you do is you take your peak to peak value and multiply by 0.3535, and then you get your RMS value. Say if we take the 28.7 volts peak to peak and multiply that by 0.3535, I get 10.14 volts, which is close. It's not the most accurate. Alternatively, to get the RMS, you take the V max, which is about 14.3 volts in this case. Doesn't matter if it's negative or positive. You just the absolute value. So I'd say about 14.3 volts, and then you multiply that by 0.707, and that'll give you your. I got 10.1, but it's around about that, and that's how you convert that. Basically, to convert back from RMS to peak to peak, you basically divide your RMS value by 0.3535, or if you want to get the maximum value of the one peak, then you just divide your RMS value by 0.07, and that's how that works. Now this is the pure AC. It's not been rectified or regulated, so next we'll add some rectification diodes on it and make a crude bridge rectifier and see what we get out of it. A standard bridge rectifier is made up with 4 diodes. You can usually buy them as a 4-pin package, which all the 4 diodes are all already arranged for you. Or alternatively, I call it a crude bridge rectifier. It's just basically a bridge rectifier made out of 4 diodes. Now, I'd recommend using diodes such as a 1N4001 or 1N4007, something in that range, because they can handle a lot more current and they can handle a lot more voltage just in case. Now, the bridge rectifier I use in this example that I've made, I just throw in annual diodes and then they happen to get hot. But it's always best to check your diode specifications beforehand. Okay, I've added a crude bridge rectifier in there, and I've now put the meter into DC mode, and I've attached it to here, wired it in. And you can see the AC is still the same going in. That's the diagram. The idea with a bridge rectifier is, if positives go in this way, will go this way and out that way. But if negative's going in, it will go that way. And obviously the same will happen on this side, but it'll always be opposite of each other because of the way AC works. So technically you will get a DC output, but it will look a lot like that. And this will actually be at 120 Hz, which we'll have a look at in a moment when I change the meter probes over. I'd like to show both waveforms on the screen, but if I was to use a second probe, the two grounds would actually short out the measurement. So what I'll do is I'll switch the oscilloscope onto the DC output, and I'll show you what that looks like. Okay, so here we have the somewhat choppy DC output, and you can see 121 Hz, and that's due to the fact that it's switching backwards and forwards between the thing on the AC. In order to smooth that, we have to put a cap on the end. So nice electrolytic. I'll dig an electrolytic out and stick it on there and show you what it looks like. Okay, a word of caution before I go back to filming. When you're using electrolytic capacitors, make sure you always have a pair of safety glasses on, because if you get in the wrong way round or you accidentally go over the voltage, they tend to go bang and they shoot their electrolyte everywhere, and it's not pleasant to have that in the eye. So back onto the circuit. Okay, I added a 100 microfarad 50 volt cap in there. I wanted to make sure that I was doing that right. So basically what I did is I've taken this, it's hard to draw when you're looking through the camera, so, and the pen's being a pain in the bum. So there's your plus. That's what I've got right now. So let's switch it on and see what we get. You can see the cap's charging right now until it reaches the trigger point. There we go. You see, we still have the 120 Hz ripple there, but it's a lot more stable now. And that is leveling out to just above 11. So just above the 11 volts. Now I would say we'd further smooth that out with a ceramic capacitor. So I'm gonna get one. I usually stick 100 nanofarad on it, and so let's get one, stick it on, and see what we get. Okay, I'll just stick one in there. Nice reel of them here. Okay, so let's turn it on. Hasn't cleaned too much of the ripple out, but I'm sure some of the high frequency noise is gone now, which is good. Then basically we take this voltage. You see the voltage is a little bit more stable now. And what we do is we now take this this voltage now, and then we stick this into a regulator, whatever type of regulator we're going to use. I would use a 7805 for logic, or we'd actually feed this into our power supply, and that's what we'd use. But I'm going to show you using the 7805. So I'll dig that out next, and we'll come back to that. Now, as a quick introduction of the 7800 series, what we'll be looking at, what we'll be focusing on in this video will be the 7805, which is the 5 volt version. It also comes on 7806, 70808, 70809, 7812, 7815, and I believe there's others as well. And those are 6, 8, 9, 12 and 15 volts respectively. These are fixed voltage regulators. You do get ones that are adjustable, and we'll be talking about that in the next analog video. And you also get negative ones, which are the 7-9 series, and they also follow the same convention. And all the TO220 packages all have the same pin out, which is in, ground, out, which I'll be showing in the next video segment. And these chips are very common, and they're very easy to use, and good for any hobbyist. Okay, the 7805 regulator, if I can get a decent shot of it. There we go. Now this one's made by On Semiconductor, but most of them are the same, depending, but it doesn't really matter where you get it from. Now the data sheet I have on the screen right now is from Motorola, but basically I could explain this is the 3-terminal regulator, output current up to 1.5, but I'd usually not push it past 1 amp because they do get pretty hot. So basically you need to put in at least 2 volts more than the required output voltage, which in this case is a minimum of 7 volts, up to 25 volts for this particular version. But I like to keep between 7.5 and 17 volts for my my 7805 circuits. Well, this is always something good you'll want in your toolbox, in your bits box, definitely. I always keep a small stocking supply. I usually keep them in the 10s at least, because they always pair up well with any 7400 logic or PIC or any Atmel type things. Anything you need a 5 volt, that's for me. I just slap it in there, and that's what it is. It's good for that. Okay, I've added the 7805 here. Drew it on the diagram. See, the pin out for this device from left to right is in, ground, then out. So basically, in you put your input voltage, ground goes to ground, and out is your output. I put a 100 nanofarad cap across the output because that's convention, that way it reduces any ripple. Now I've hooked up the oscilloscope and the test meter to the output. Let's see what we get. 5.1 on the meter, and this scope says about 5.2, and it's a nice clean signal. So that's how we end up and get a nice clean 5 volt signal for logic supplies. That concludes the Linear Basics episode, the episode 2 of the Power Supply Design series. I hope you enjoyed it. I hope the information was useful. Now, next episode, episode 3, will be a digital episode because it's an odd one, and it will be the MCP 4822 12-bit DAC, and we'll be looking at driving one of those with the Arduino. And following that, in episode 4, the next analog one, which will be part 2 of my Linear Basics, and we'll be concentrating on the LM317 adjustable regulator, which is an old favourite, and we'll be talking about the pros and the cons of such a device, and we'll also see it in action and have some fun with it. Thanks for watching, please like and subscribe, and I'll see you next time.